Good morning, everyone. So, before we are going to start the class, today's discussion, let me ask you whether you have received any time duration for which you need to come to the campus. Some of you have told me earlier that it is only from 25th of February you are supposed to start to return to your campus. Am I right? Can anybody please
Yes, sir.
confirm? Okay. Do you have any limitation that it is from 25th to 27th or a time duration has been given?
25th to March 15, I guess.
Okay, because what I am asking that the time when you are going to come to the campus, maybe you will be not be coming, all of you will not be coming only one single day. So I have to continue the class because it is already scheduled that 12th of the March is the last class for the theory. Okay. So if I want to, that's why I'm taking some extra classes, and I have also given a request in your WhatsApp group about shifting the 15th extra class supposed to be, and that was supposed to be on 15th. If it is possible, I'll be taking it on 17th. So the problem is that as the class will be going on, and I cannot stop the class at this point. So if most of you are traveling during 25th to 27th, and if you are going to miss the class, that will be a problem for you only because I cannot stop the classes. I hope you can understand. So that's why I tried to ask you if that is because 25th February to 15th of March is a very long window. Okay, and you are total 34 students. So if it is only 2 or 3 days, that then and you are telling that okay, only one single day, so many students are just transferring from their home to college, then I can probably excuse that day's class. Okay, but if it is of a long range, I cannot leave the class. So that's why I need to ask you. Okay. Now, related to the discussion, see, I have discussed the note one, the basic fundamental theories for storage and the history and the flow parameters. This note two is also giving you some brief idea about some of the background, which we have not seen earlier, and this is obviously based on the experimental and the modeling part or the more or less after you have known the theory part, then only you will be able to understand these things. Okay, so don't read note 2 and note 3 first. Okay, after this note 2 discussion, I'll be again discussing note 3, which is the appendix, and I will be discussing with you the methods of experiments, and I'll be showing you some of the graphs, some of the data, so that you can understand, you have a clear idea about how the experiment and the interpretation are going to be done. And finally, I'll be discussing with you some specific papers, not more than 5, hopefully, so that you can correlate that what are the work is going on globally, important work, and how your teaching or how your learning can help you to orient yourself in that direction of your higher studies. Okay, and if you want to pursue this in your master's or your PhD level later, so then you will be having some idea about this particular subject if you want to do further research on this subject. Okay, so uh, in the earlier class, we have discussed about the ECBM, which was not discussed earlier. ECBM is the enhanced coal bed methane production or the enhanced coal bed methane recovery. Okay, and it is the ECBM process by which we can increase our recovery rate from approximately 50%, which is the limitation in the conventional CBM reserve and the normal CBM reservoir, to 85% to 90%. Okay, and what are the two methods? There are actually three methods. The three methods are pure N2 injection, pure CO2 injection, and then a mixed volume of N2 and CO2. And you have also seen that there are some pros and cons of all the methods. So you need to remember those things. And in this note, I have tried to give you in a very brief idea, which will be sufficient for you at this stage. The detailed analysis and detailed discussion I am excluding for you. Okay. So you don't need to go for any other discussion on this background. And we have also seen that how the different techniques can help in the production. Okay. And so there are different types of isotherm graph also, and we have seen that there are 6 types of graphs, and when each of the graphs will be very much important for you. Okay, so you need to know that also. The standardized graph for isotherm. Today we'll be starting with the basic theory of the adsorption. Okay, earlier we have seen only the definition, the theory of resorption and chemisorption. Now we'll come to different principles that are going to govern, that are going to be observed during the coal and gas interaction. Okay, generally it is we are dealing with the coals. That's why we are calling about telling about this coal. We are talking about this coal, but in general, this is true for every porous media. Porous media means the medium which is having porosity into it. Okay, it may be coal, it may be shale, it may be other tight reservoir. Okay, it may be of clay also. It is also observed. But as we are dealing with the coal bed methane, so we'll be discussing every time from the coal perspective. Okay. Now, in general, there are 3 important concepts. Okay, as you can see, first is the physical absorption into the internal surface. Second is the gas molecules, they are adsorbed from depending on the pressure into the internal coal molecular structure. And the third concept telling you that adsorption in the form of layers in the different pore spaces of the coal matrix. Now, coal matrix you have already learned. Okay, each 3 different principles is discussed with 3 different theories. There are some other theories, but these 3 theories are the important one. So that's why I have excluded all other theories and only limited to 3 theories for you. The first one, you have some idea, it is the Langmuir theory. It is the Langmuir theory, and in the Langmuir theory, you already have seen that the Langmuir theory is related to the coal and gas interaction, assuming that there is a monolayer. That means the adsorption is taking place in a single layer, and it is also assumed that all the pore spaces inside the coal, they are energetically homogeneous. That means all are having the same energy to adsorb the gas molecules. And more specifically, each pore space can adsorb only one molecule, and there is no overlapping or there is no overlapping criteria about or governance about how one gas molecule will be absorbed into one pore spaces and how their surrounding moles are going to be absorbed. So there is no overlapping. It is mutually excluded or mutually independent about the pore size into the coal and how the gas molecules are to be absorbed into that pore spaces. Okay. Energetically homogeneous means all are having equal importance or equal priority to absorb the gas. Just like in the statistics, you must have heard the concept of IID, independent and identically distributed. I hope you understand the terminologies. Okay, identically means all are the same, and independently distributed means it is mutually excluded. Okay, there is no overlapping. So similar concept is applicable for here. And the equation you have also seen earlier, that V is the amount of the gas adsorbed at some particular pressure, is given by this equation, where VL is the Langmuir constant. It is called the Langmuir volume. Langmuir volume is the maximum amount of the gases that the coal can adsorb at a particular temperature and pressure. Okay, the temperature is constant. That's why it is called the isotherm graph. It is infinite pressure at which the maximum absorption is done. Okay, so if you see the isotherm graph, let me show you. Let me go back. This is the type 1 and this is the general form of the Langmuir. It is also called the Langmuir graph, as you have shown, as you have known earlier. Now this, you can see that at increased pressure or the increased relative pressure means it is a fraction of the maximum pressure with the different stage pressure, okay, experimental pressure. So it can vary from 0 to 1, and then you can see that after a certain time it is going to be flat. That means the maximum absorption at that temperature and pressure which is possible, it is already done. So no further increase. That means whatever the gases are present, the gases has already taken all the pore spaces, and that means at that temperature and pressure condition the coal is saturated with the gas. That is very important concept. If it is not saturated, then the moment the pressure is going to increase, the graph is going to be increasing. Graph should increase. It is only possible because the coal is saturated at that pressure, at the pressure and temperature, not only pressure and temperature. If you may decrease the temperature, it may increase the absorption quantity. Okay, so this is the shape of the isotherm, and this type 1 graph is also notified as the Langmuir graph also for coal, and this is very much common for the coal and gas interaction. Okay, this P is the normal experimental pressure, and if you when I'll discuss the experimental step, you will see that at uniform stages you are going to increase the pressure, suppose from 0 to 6 megapascal. Okay, and so at each uniform 6 stages are going to be considered. Suppose the first stage is 1000 kilopascal, then 2000 kilopascal, or 1 megapascal, 2 megapascal, 3, 4, 5, and so finally the 6. So uniform stages, uniform pressure stages. Okay, and the maximum pressure is 6000 kPa. So the relative pressure, if you are going to discuss this as they have discussed there in the P by P0, so for first step it will be 1 by 6, for second step it will be 2 by 6, and so on, and finally it will be reaching 1. That's why I am telling that the ratio of the relative pressure is going to vary from 0 to 1. The PL is another constant which is called the Langmuir pressure, and as you have seen earlier that the Langmuir pressure is defined as not the pressure related to the maximum volume, but it is the pressure related to the 50% of the Langmuir volume. Let me repeat once more. Langmuir pressure is defined as the pressure corresponding to the 50% of the Langmuir volume, which is the maximum volume that can be absorbed by the coal at a particular temperature pressure condition. Okay, so that is called the Langmuir pressure. And you have also seen earlier that with temperature, it is not the Langmuir pressure is more or less same, but the Langmuir volume is going to differentiate. That's why the temperature has a indirect influence on this gas absorption capacity. Okay, and so sometimes this equation can be also written in this form as given as 2.5. Okay, where PL 1 by PL is considered as a constant B, which is called the Langmuir constant, whereas the PL is the Langmuir pressure. Okay, and pressure is having the same unit as either by PSI or megapascal or kilopascal, like that. Okay, so this is the brief condition of the Langmuir theory. In this figure 2.8, you can see that the first figure of each individual pores, there is no such a layer formation. Only one molecule is going to be adsorbed at one surface. So that is the concept of the Langmuir case. Okay. The next theory is the BET theory. Brunner, Emmett, and Taylor, three scientists or three researchers, they have designed this theory. They have done the experiments and they have proposed this theory. What they are telling, they are going to extend this Langmuir model for multi-layer. Langmuir theory is fixed for single layer, but they are considering this Langmuir model with all the assumptions of the Langmuir model, and finally they are going to proceed this for multi-layer formation. So this BET theory is obviously an extension when the adsorption is taking place from the gas coal interaction and the adsorption is taking place into monolayer to multi-layer formation. Okay. You can also see that I have highlighted some of the parts of it, which is very much important. It assumes that in addition to the assumptions of the Langmuir model, each adsorbate molecule in the first layer serves as an adsorption site for the second layer to the third layer, and so on. That means you can see the figure B. I hope you can see it. Okay. You can see the figure B in the Langmuir case, whereas only one single layer has been formed. In the BET theory, you can see that there is a layer by layer. So you can see that there is already 3 and 4 layer. So the first layer is the giving the contact, and then the gas is going to be adsorbed. The second layer is adsorbed from the first layer. So the first layer will be acting as a adsorbed molecule. The adsorbed molecule in the first layer will serve as an adsorption site for the second layer to be adsorbed. Then similarly, third layer, fourth layer, like that, and it will be formed a multi-layer. Okay. The attractive forces between the adsorption molecules are very weak or negligible. Attractive forces between the molecules, so that they cannot attract each other. Okay, for forming any scattered layer. Okay, so there is no individual attraction, and the attraction, if it is present, it is very negligible. And the heat of the adsorption of all the layers, intermittent layers, are assumed to be equal for the heat of the condensation of the adsorbate. Heat of the condensation means adsorbate is the gas. Condensation means how it is going to be solidified, because it is the exothermic reaction, adsorption, you have already seen. So when the temperature is going to release, it will be cooling down, and so some of the gas may be going to be condensed. So that heat of condensation is going to be assumed equal for all the first layer, second layer, third layer, and so on. Okay, the general expression, the equation is given by this. Okay, whereas the Vm is the monolayer volume of the coal. Okay, C is a constant, which is the equation constant, which is depending on the concentration of the layer, capital C. P0 is the saturation vapor pressure. I am going to define. Saturation vapor pressure is defined as the maximum partial pressure exerted by the air. You can see the saturation vapor pressure defined. Saturation vapor pressure is defined as the maximum partial pressure exerted by the air saturated with vapor at a particular temperature. Now, this saturation vapor pressure, obviously, if you are going to tell that it is saturation vapor pressure, so you must have understood that the vapor is already saturated. Okay, the coal is already saturated with the vapor, and that's why the saturated vapor pressure has come. And whatever that adsorption is the two-phase operations. So in the solid phase and the liquid phase, or the gas phase, the maximum pressure that is given, and this pressure is not a total pressure, as there are two different phases. It will be a partial pressure. That's why the partial pressure terms is coming. Okay, and so depending on the saturation, and as the saturation increases, the partial pressure, the mole fraction of the vapor will also increase, and so as the mole fraction will increase, the partial pressure is also going to increase. So that's why this maximum term is coming. Please try to understand the importance of each of the terms. Okay, so the saturation vapor pressure, it is fixed with some particular temperature, because if you are going to change the temperature, some of the water or some of the fluid may get evaporate, or some of the fluid may get condensed. That's why a particular temperature is coming. It is a mixture. That's why the partial pressure is coming, not the total pressure, and the maximum partial pressure, because it is the saturation pressure. If you are not going to, if it is saturated, so you are not going to take the average one, you have to take the maximum pressure one. That's why this saturation vapor pressure is having the maximum partial pressure concept with a particular temperature. Okay, and P, normal P, is the experimental pressure at the step of your experiments, the way you are going to take the pressure steps. Suppose if you are going to take the pressure steps from 0 to 6 megapascal, you may assume that the pressure is the 0, then 1 megapascal, then 2 and 3, and so on. Okay, the more value of the C, the more it will denote the concentration, and so the concentration will increase. That will dictate, that will show that the more formation of the multilayer has been occurred, is occurring. Okay, the more higher value of the C, it will denote that the more layer formation has been taken place. Okay, now this BET equation, okay, BET equation as an extension of the Langmuir theory, it is not always valid. Okay, it is valid, you will see that it is valid with a certain pressure range. As you can see, I have highlighted from P by P0 from 0.06 to 0.35. So only one third of the total pressure range is valid for this, verifying this BT equation. Then you can ask the direct question that if it is not valid, if it is not going to give the results according to the principle for the 2/3 of the pressure stages, then why we are going to follow? But then comes the its simplicity. The BET equation can discuss of all the among the 6 types of the isotherm graph. It has the maximum capacity of this of describing any 5 types of the isotherm graph. Okay, except for the Langmuir graph, because it is for the monolayer. It can describe all other 5 types of graph. Okay, that's why it is very much universal acceptance. It has a universal acceptance, and so it is going to be used globally. Okay, generally you will see later that whenever you are going to relate the pore size distribution within a porous media, maybe a coal, the pore size distribution means in the total pore network, how much fraction is the macropore, how much portion is the mesopore, and how much is the micropore. To see these guidelines, if you are going to plot, okay, you will be able to see that what fraction of the pore is related to your coal. Okay, and in that case, it is the BET equation is going to be useful. Okay, generally for micropore adsorption, small micropores, CO2 is used, whereas for the macropore adsorption, N2 is used. Okay, I'll discuss some brief concept of these 2 theories of macropore and the micropore adsorption or the process later. Okay, so now you should know that even if it is not that much valid for total range of the experimental pressure, but then depending on the simplicity and depending on the importance of its universal acceptance of all other, to discuss all the other type of isotherm graph, it is commonly taken as a globally used. Okay, it is globally used. Next one is the important one. It is called the Dubinin and Polanyi's theory. Dubinin is the earlier researcher who has given the concept, and Polanyi has somewhat modified it and given some extended this theory to give some other concepts. What is the difference of this theory? And I am not going to discuss the difference of each of this theory. It is your task. Okay. So if I ask that what are the difference in concept or what are the similarities of this theory, you should be able to learn by yourself, and you have to give the answer. Okay. I am not going to discuss the comparison of these 3 theories. Similarly, for N2 ECBM and the CO2 ECBM, you have to understand the differences and you have to write if the question comes. Okay. Next one, let us discuss the Dubinin-Polanyi's theory. Now, earlier these 2 concepts, we are going to discuss that we have assumed that it is the monolayer or the multi-layer surface. Okay, just showing you this figure again. So in this figure, you can see that it is a flat surface. Okay, and this is a monolayer for Langmuir, and this is a multi-layer formation or transition from the monolayer to multi-layer in the BET equation. Dubinin, however, proposed that it is not the same case as it is exposed like this, whereas the pore volume, the pore spaces are just like a storage space where each of the gas molecules will just fall down because of the adsorb potential. Because of the adsorb potential. What is adsorb potential? In the electricity, you may have a thought about the electropotential. Okay. So the similar concept is the adsorption potential. So that means each of the molecule based on their adsorption potential or potential energy depending on the adsorption, if I say so, they will fall and they will be adsorbed in the same way. They will be falling into the pore spaces and thus they will be going to be adsorbed. There is no such layer formation, but the pores are but the gas molecules are falling depending on their adsorption potential capacity. Okay, so this adsorption potential capacity is the concept that is given by the Dubinin first time, and then what their adsorption potential actually means, it is associated with the dispersion forces. Okay, it is associated with the dispersion forces, as you can see in this, I have also highlighted, and they are enhanced into the microspores. They are enhanced in the microspores due to the overlapping of the absorption field from the opposite pole walls. Now this is significant because in the earlier concept they have not considered the overlapping charges or overlapping characteristics, but it is in the simply in the Dubinin theory they are going to consider the adsorption potential from the surrounding pores also. Okay, and then mixing with this adsorption potential mechanism with the volume filling concept, that it is a pore spaces, and with this adsorption potential the volume, the pores, the gas molecules will be just falling and they will be filling the void space, and that is the concept of this Dubinin theory. Here, the potential field is existing around the surface of the solid, okay, where the gas molecule will come and interact with and they will be creating the adsorption potential depending on the potential field existing surrounding the solid, okay. And the adsorption potential they are going to define as the work done per molecule per mole of adsorbate. You can see the adsorption potential is defined as the work done per mole of adsorbate to transfer molecules from the gaseous state to the adsorbed state. Gaseous state means the free state where the random motion is occurring. So that means the adsorption potential is related to the work it has to done from taking the gas molecule from the free state, and related to the adsorption potential, how much of it will be going to be adsorbed or how much of it going to be filled in the pore spaces in the adsorbed state, and that work done is considered. Okay, and this work done is mainly due to the temperature independent dispersion process. So now you can see that although it is an adsorption theory, but this is the first time they are going to give a temperature independent dispersion process. That means the adsorption is now going to be independent of the temperature. Okay, that means the volume is fixed, because the volume in the adsorption potential in a coal, the total porosity is independent of temperature. Okay, so the temperature independent concept is also considered here. Okay, now they are going to express the first concept of the adsorption potential A with the volume adsorbed, because as much of adsorption potential will be there, the volume will be adsorbed that much. Okay, and this particular concept is also fixed for the gas solid system, and it is called the characteristic graph. I am coming to later what is the characteristic graph. This A adsorption potential is again going to be governed by this equation 2.8, where R is the universal gas content, T is the absolute temperature of adsorption, okay, and the P0P is again the defined pressure step. Now you can tell that, okay, first they are telling that it is due to temperature independent dispersion forces, and again you are going to consider the T. The temperature independent dispersion forces are coming because just like the concept of the van der Waals forces or the chemical bonding, the strong bonding which is independent of the temperature related temperature variation. But as we are going to consider the volume, so when you are going to consider the volume, and the volume is a function of the adsorption potential, so that's why you are going to consider the temperature again. Okay. Now, this equation 2.8 is called the characteristics graph. Okay, why characteristics graph? Because the characteristics of the volume given by 2.7 is only depending on a gas content of gas constant R, universal gas constant R, T at a particular temperature, and the ratio of the pressure. Okay, so you can see you are not going to vary the temperature, you are just going to vary the pressure, and you will be getting the characteristic graph. So if you have the idea of this equation, that means you are going to define that type of adsorbed gas, suppose methane, and a particular type of coal, and with changing the temperature T, okay, changing the temperature T, having the same P0 and P, you can calculate A. So with the data of only one temperature, the pressure data of only one temperature, you can calculate as much as adsorb potential for that particular gas and coal system for different temperature. That's why it is called the characteristic graph or characteristic equation. That is the plus point or the significant important point of this Dubinin theory. Okay. Now, with this Dubinin theory, okay, Dubinin has suggested, Dubinin has explained that this adsorb potential, the micropore volume is going to be filled first due to the mechanism of the volume filling and not by the any monolayer formation of the pore surface. So that's why if you imagine each single pore with their adsorb potential, they are coming into the micropores and they are going to fill. The gas molecules are coming and they are falling down into the micropore of the solid coal. Okay. Then Polanyi's theory, Polanyi has given this, modified this, okay, and he is going to tell that okay, this concept should be extended about the volume filling theory and this adsorption potential theory, and they have given two different equation, okay, this Polanyi's theory, and with this equation some other researchers, okay, they have act on these two theories, okay, and they have given two different equation, which is the first equation is called the Dubinin-Astakov equation, which is given by equation 2.9. You can see the 2.9 is called the Dubinin and Astakov equation, which is given by the expression 2.9. V is equal to V0. V0 is the volume of the micropore. K is a constant. P and P0 are the same as the experimental pressure and the saturation vapor pressure respectively. N is a heterogeneity parameter related to the coal, which is varying from 1 to 4. And this K is also important. K is a constant of the particular type of the gas and particular type of the coal or other rock. Okay, and this is measured again from RT beta E, where R is the universal gas constant, T is the absolute temperature, E is the adsorbed potential concept. Okay, E is the characteristic heat of the adsorption, and beta is the adsorption affinity. Affinity means how strongly the gas and the coal are attracted to each other. That is going to change the beta, and E is the characteristic heat of the adsorption, which is going to emit. So this equation, if you are going to take N is going to vary from 1 to 4 based on the coal heterogeneity parameter. So rather than this, another scientist, Raduskevich, he has studied and he has modified this equation and suggested the Dubinin-Raduskevich equation, where only N value is fixed. So equation 2.99 is having 3 unknowns, but equation 2.10 is having 2 unknowns. What are the 2 unknowns in equation 2.10? It is the V0 and the K, because 2 is already fixed. And how to calculate this? If you are going to iterate, if you are going to take certain steps and you are going to iterate by software, you will be going to get the value of V0 and K, and from that equation of RT by beta into E, you will be able to calculate the E, characteristics heat of adsorption. Okay, so it will be giving you a lot of information about the system, about the particular coal and gas systems. Okay, and so as you can see, they have also explained that the unique advantage of this theory about the characteristic graph. So please read this. Okay, this is very much important. Now for the factors. Okay, for the factors, as you can see, I have already discussed with you about the factors of coal rank. This is the first, the coal rank. Okay, coal rank you already know, and so I'm skipping this. Okay, the coal rank and this ash and mineral content, all of these things, you know, moisture content, you have read this in the, when I have discussed about the proximate analysis, how it is going to affect the type of the adsorbate gas, whether it is methane or carbon dioxide or nitrogen in a smaller. Okay, then the temperature. Okay, temperature, I have also discussed these things when you are going to see first in the Langmuir parameter, the VL and the PL. Okay, then so these parameters, I'm just skipping, you need to read it. Okay, from here, or you can read it from the note 1 also. Next comes the last discussion for this note. It is the effect of the gas option in coal, shrinkage and swelling. The shrinkage and swelling, you have already read the rock mechanics. So you know that shrinkage is related to the volume contraction and the swelling is related to the dilation or the increasing volume when the pressure has been applied to the surroundings, to the surrounding of the coal. Okay, pressure or stress, sorry. What is the difference between pressure and stress? Anyone? Can anybody say directly what is the difference between pressure and stress? I don't know if somebody is here or not, or most of you have just put this on and left. Can anybody tell me what is the difference between pressure and stress? Anyone? Some of you has already put the microphone into hold, na? Very smart. I can see that some of you have put it into hold. Karthik Gupta, then Chakrapani. Okay, so you are very smart. That you have just put it and put a hold and then doing your things, or maybe sleeping also. Who knows? So nobody can tell, or nobody is here. Anyway. So this shrinkage and swelling effect. This shrinkage and swelling effect is also important related to the gas absorption, because depending on this shrinkage and swelling effect, the volume, the adsorbed capacity is going to change. Okay, there are a lot of other variations also. You have earlier seen that the permeability is also going to change based on this shrinkage and swelling. So this effect is very, very important, and there are a lot of work has been done to estimate this shrinkage and swelling. So what is the concept? Now, depending on the rock, you will have seen that taking the rock as an elastic medium, application of the surrounding stresses or the overburden stresses, which will create the volume expansion or the volume contraction. If it is confined, so obviously it will be contracted. If it is unconfined, so obviously one direction in the UCS case we have seen that if the one direction there is an extraction, there is a contraction, the opposite direction there will be an exchange or extension. Okay, and this is the way by which we are going to calculate the Poisson ratio. But then in case of C-beam reservoir, you know that this is the case of a, although the coal is also elastic, but then depending on the gas absorption, the just like the pore pressure. Okay, you also know the environmental effect and the effective stress principle. So when the gas molecules are being adsorbed into the coal, the pore pressure going to increase. So with this increasing pore pressure, the surrounding stress or the effective stress will be reduced because the pore pressure is going to increase. Okay, so vertical and other principal stresses are going to reduce, and so the effective stress is going to reduce, and so when the stresses are going to reduce, the contraction will be less. Whereas if the pore pressure is going to be very much small, nearly zero, when the gases are going to be dissolved from the place, or when the saturation of the water inside the pore, very much a less saturation is there. So obviously the pore pressure being zero will indicate that the effective stress is very high, as much as the the original value of the overburden stress or the other horizontal stresses. Okay, so in that case, whatever the contraction or the shrinkage will be take place in the in situ, that will be the maximum one. Okay, so this concept of this adsorption and desorption in a CBM reservoir is very common depending on the pressure up down, depending on the gas production. Okay, and so in the gas production it is totally desorption, so it is going to swell, whereas when you are going to inject the gas, it is going to increase the pore pressure, so it is going to it is going to swell, and whenever you are going to dissolve it, it is going to shrink. Okay, now this effect, this shrinkage swelling effect, is occurring depending on the two phase concept. Okay, it can be explained by the two reasons. Okay, first is that the adsorption of a liquid like layer on the pore walls, which can create a pressure gradient large enough to change the internal structure of the coal. So whenever there is a shrinkage swelling effect, you know that this effect can change the internal structure of the solid system, here the coal, depending on the liquid layer surrounding the pore walls. The second condition is that imbibition of the fluid into the coal result in the relaxation of the molecules from the coal. As the fluid molecules are going into the coal, there may be some of the coal fragments or coal molecules or the coal parts are coming out of that system or that coal matrix. So this interchange is also going to reduce the bulk volume. Okay, so that's why the bulk volume of the coal matrix changes, and hence the aperture of the coal cleats are also going to increase and decrease with the time, which in turn changes the coal matrix and the fracture permeability, and so the matrix porosity and the outside secondary porosity, the fracture porosity. Okay, so this is very intricate issue for the coal bed methane production or the ECBM process, because whenever you are going to see this shrinkage and swelling, there is a lot of work has been conducted, but it is very difficult to estimate because it is very less for at low pressure, but it is very much significant at higher pressure. It can happen as much as 10% or 5%. Okay, for methane is it very less, but for carbon dioxide it can happen in 10% or more than 15 or 20%, depending on the pressure temperature condition. Okay, and obviously the gas property. Next is depending on the concept of whether it is saturation or undersaturated or the partial saturated, that is also going to be take place. Okay, and then depending on the adsorbed gas, for helium there is no case of, because helium is not going to adsorb. For nitrogen it is very small, so you may not be able to estimate the shrinkage at all or the swelling at all. For methane it is again somewhat higher than nitrogen, but still it is less than carbon dioxide. But for carbon dioxide it is significant. Okay, so again the variation of these adsorbed gases, they are going to dictate how much the changes will be done for the shrinkage and swelling. This shrinkage swelling degree, that means the amount, can be very significant, and so it can directly affect your gas production. And the gas production, if the gas production is reduced, so obviously you are going to get the less fuel. So that's why your production is going to hamper. Okay, in globally the effect of permeability, because the shrinkage and swelling is directly going to give you the effect on the permeability. If you remember in the permeability class of your rock mechanics, the permeability is very much sensitive, and it is very much sensitive with the aperture, and it is going to relate with the third degree of the aperture. That means if the aperture is little bit small, okay, the permeability is going to reduce. The permeability is also going to reduce 3 times, not the 3 times, in the 8 times. Sorry, suppose it is going to be half, so permeability is going to be reduced 8 times because there is a cube relation. You can also check. Okay, and conversely also, if the permeability is going to be, if the aperture is going to be double, so the permeability is going to be increased 8 times. That's why you have seen that all the permeability graphs, if they are going to report it in that note 1, and in the later stage also you will see that all the permeability are expressed in log graphs or the semi-log graphs, where permeability is always considered in a log range, and generally there is a 10 to there is a 100 to 1000 times of increase from the original state to the later stage. Okay, so significant amount of changes in permeability is observed, and this is not only due to the adsorption. There are other processes, but the main concept is that whatever is happening, there is a pressure change, there is effective stress reduction or effective stress concept, then there is a fracture porosity reduction, then there is a compressibility of the fracture, then there is a gas or water situation effect, and obviously there is a everything coming together with the shrinkage and swelling, because this is directly working on the gas volume, coal volume. Okay, so that's why this discussion, this shrinkage swelling is very important. With the so with this, your note 2 is coming to an end. Now in the next class, I'll be starting with the appendix A, note 3. I have already uploaded into your discussion. Okay, you please check, download it, and we'll be starting this in the from tomorrow Friday is at 8 a.m. class. Okay, so any questions for anyone? If you want to have any questions, please ask. And please tell me about whether you are going to take the class on, whether it will be okay for you on Wednesday's class or not. Okay, so I'll be then fixing this time. Okay, and I'll be notifying in your WhatsApp group. So please, by the end of the today, let me know about your decision, whether you are able to want it to at 11 a.m. or 10 a.m. or 9 a.m. at what time. So no questions.